Long ago, before the birth of stars or the concept of time, there were questions so vast that even the universe itself could barely understand them. Among these questions is one that defies the limits of human imagination. What if our universe, this magnificent and endless expanse, is nothing more than the interior of a colossal black hole? It is a question that cannot be easily answered, a puzzle that has occupied and inspired philosophers and scientists for generations. And now, in an age when human ingenuity has given us eyes to peer into the darkest corners of space, we may be on the cusp of an answer. At the center of some of the most dramatic cosmic phenomena is the black hole, a structure so mysterious and powerful that it has captured the imagination of scientists and the public alike. Imagine the universe as a vast tapestry of galaxies, stars, and planets, all connected by fundamental forces. In this complicated cosmic dance, black holes stand out as powerful anomalies. Places where the gravitational pull is so strong that nothing, not even light, can escape once it crosses a boundary known as the event horizon. This makes them invisible to the human eye and only detectable through their dramatic effects on the surrounding matter and light. The concept of a black hole is not just a product of modern science fiction. It is deeply rooted in our understanding of physics and dates back to Einstein's general theory of relativity, which showed how massive objects can distort the fabric of space-time itself. When a star, many times the mass of our sun, uses up its nuclear fuel, it collapses under its own gravity and forms a singularity, an infinitely small point where density and gravitational forces reach extremes we cannot fully understand. Around this singularity is the event horizon, not a physical surface, but a spherical boundary beyond which escape becomes impossible, even for light. The gravitational pull of a black hole is so powerful that it not only distorts the trajectories of nearby objects, but also bends light itself, leading to fascinating phenomena such as gravitational lensing. This effect causes the light from stars located behind a black hole to bend around the hole, sometimes forming rings of light or multiple distorted images of the same star. A true marvel of cosmic optics that has become a powerful tool for astronomers to detect and study these hidden giants. But not all black holes are the same. Some are stellar black holes, a few times the size of our sun, formed by the collapse of individual stars. Other, much larger, are known as supermassive black holes and are located at the centers of galaxies, including our Milky Way. These giants can be millions to billions of times more massive than the sun and play a crucial role in the formation and evolution of galaxies, acting like cosmic engines that propel matter and energy through vast regions of space. These mysterious cavities of gravity challenge and enrich our understanding of the fundamental laws of physics. They are natural laboratories for extreme physics, places where the forces at play challenge our established theories about how the universe works. The recent observation of gravitational waves, ripples in the fabric of space-time created by the collision of black holes, has opened up a new way for us to study these enigmatic objects. Through such observations, we gain insights into the nature of gravity, the behavior of matter under the most extreme conditions, and the structure of space-time itself. Scientific background. To truly understand the mysterious attraction of black holes, we must start with Einstein's general theory of relativity. Think of this theory as a master key, a key that unlocks the secrets of gravity, space, and time. According to Einstein, mass not only exists in space, but it deforms space-time itself. Black holes are the ultimate manifestation of this idea, regions in space where gravity is so strong that it pulls everything, even light, into an abyss from which there is no escape. These are places where our known physical laws break down and our usual concepts of time and space simply no longer work. It all starts with a massive star. When such a star uses up its nuclear fuel, the external pressure that once kept it from collapsing is no longer there to counteract its immense gravitational force. The result? The star collapses under its own weight until it forms a singularity, a point of infinite density where, frankly, everything we think we know about physics collapses. Surrounding this singularity lies the event horizon, a boundary that acts like a cosmic one-way street. Nothing that crosses it ever comes back. Beyond the event horizon, even light is helplessly exposed to the unstoppable pull of the black hole. The gravitational influence of a black hole affects not only nearby stars or stray planets, but also the nature of space-time around the hole. The force of attraction distorts the light, creating a phenomenon known as gravitational lensing. Imagine a beam of light that has traveled billions of years and then hits a black hole. Instead of disappearing, the light is bent and wrapped around the black hole, creating rings and arcs that seem almost like ghostly echoes of the distant universe. These echoes are one of the most compelling pieces of evidence for black holes, visible proof of their incredible gravitational influence. It's one of the few ways we can truly see these monstrous entities, by watching them change the universe around them. But the formation of black holes is not limited to the death of stars. The best-known mechanism is the collapse of a massive star into a black hole, but that is only one piece of the cosmic puzzle. Imagine massive gas clouds in the early universe collapsing directly into black holes without first becoming stars. Or imagine the dramatic collision of two neutron stars merging in a spectacular, violent embrace that culminates in the formation of a black hole. These processes demonstrate the versatility of nature, which is capable of creating black holes through a variety of cosmic dances. Black holes also come in many shapes and sizes. Those that have formed from collapsed stars are called stellar black holes. Although fascinating in their own right, they are overshadowed by the true giants of the universe, supermassive black holes. These colossal structures, millions or even billions of times more massive than our sun, sit like cosmic monarchs at the centers of galaxies, dictating the movements of stars, gas, and even entire galactic structures. The Milky Way itself has one of these titans at its center, Sagittarius A, a gravitational powerhouse that plays a crucial role in the dynamics of our galaxy. These supermassive black holes are far more than cosmic curiosities. They are the architects of galaxies and influence star formation, galactic rotation, and even the fate of the universe. Studying black holes is not just about the influence of gravity or sheer mass. Black holes are extreme laboratories where we can study forces and conditions that we could never replicate on Earth. A crucial breakthrough in our understanding of black holes was the observation of gravitational waves, tears in the fabric of space-time caused by some of the most violent events in the universe, such as black hole mergers. Einstein predicted these waves over a century ago, but it wasn't until 2015 that we finally detected them, confirming that the universe itself trembles and shakes when black holes collide. These gravitational waves contain information about the black holes that created them, about their mass, their spin, and even the nature of the collision. Yet despite everything we know, black holes remain a mystery that may hold the key to understanding our origins. What if black holes are more than just stellar remnants or galactic architects? Could they be portals to other universes? What if at the heart of every black hole lies the seed of a new universe, a new Big Bang waiting to explode into existence? The singularity that constitutes a black hole is strikingly similar to the singularity that marked the beginning of our universe. Perhaps black holes are not ends, but beginnings, gateways through which matter, energy, and information are reborn, reshaped, and recycled into something entirely new. The possibility that our own universe could lie within a black hole is not just a theoretical exercise, but a revolutionary idea that forces us to rethink everything we think we know about existence and reality itself. If this is true, it would mean that our universe is part of an endless chain of universes, each emerging from the depths of a black hole, and each containing black holes that in turn give rise to further universes. This is a concept that is difficult to grasp, but which makes the study of black holes all the more important. These cosmic voids, these star graves, could actually be the womb of creation. As we continue our exploration, we must grapple with the incredible mysteries that black holes pose. They are not just anomalies to be explored, but also profound symbols of the infinite potential of the universe, places where everything we know collapses, and where perhaps everything begins anew. So join us on a journey into the shadows of black holes, beyond the limits of our knowledge, to explore the limitless possibilities hidden within these mysterious cosmic giants. Types and sizes of black holes. Black holes come in different types and sizes, each with its own properties, origin, and influence on the cosmos. Their diversity helps us understand the vast mechanisms at work in the universe and the crucial role they play in shaping everything we see, and even what we cannot see. From small stellar remnants to colossal giants at the center of galaxies, black hole types tell a story that ranges from the birth of stars to the enigmatic force that drives cosmic evolution. Stellar mass black holes are the byproducts of the dramatic and violent death throes of massive stars. When a star with at least 8 times the mass of our Sun reaches the end of its life cycle, it can no longer sustain the nuclear fusion reactions that counteract its gravitational pull. When this delicate balance breaks down, the star undergoes a massive gravitational implosion, compressing all of its matter into an infinitely small, incredibly dense point, a singularity. This singularity is the heart of the black hole, a point where the laws of physics as we know them break down. Stellar mass black holes are scattered throughout the universe and often hide in obscurity, where they can only be detected by the devastation they wreak on their surroundings. These black holes typically have a mass a few to a few dozen times that of our Sun, but don't let their comparatively small size fool you. The gravitational pull of a stellar mass black hole is sufficient to distort space-time extremely. In binary star systems where a stellar mass black hole and a companion star exist in a cosmic dance, the black hole's gravity often tears material from its partner and funnels it into an accretion disk. The stirred-up matter heats up to millions of degrees, releasing intense X-rays that can be detected over vast cosmic distances. Through this X-ray radiation, astronomers have often found evidence of stellar mass black holes, cosmic ghosts that greedily feed on their stellar neighbors. The explosive death of a massive star collapsing into a stellar black hole can also lead to gamma-ray bursts, extremely powerful bursts of energy that can overshadow entire galaxies for a few seconds. These outbursts are among the most energetic events in the universe and provide a fleeting but dazzling glimpse into the otherwise hidden processes that lead to the formation of stellar black holes. Despite their long ago, before the birth of stars or the concept of time, there were questions so vast that even the universe itself could barely understand them. Among these questions is one that defies the limits of human imagination. What if our universe, this magnificent and endless expanse, is nothing more than the interior of a colossal black hole? It is a question that cannot be easily answered, a puzzle that has occupied and inspired philosophers and scientists for generations. And now, in an age when human ingenuity has given us eyes to peer into the darkest corners of space, we may be on the cusp of an answer. At the center of some of the most dramatic cosmic phenomena is the black hole, a structure so mysterious and powerful that it has captured the imagination of scientists and the public alike. Imagine the universe as a vast tapestry of galaxies, stars, and planets, all connected by fundamental forces. In this complicated cosmic dance, black holes stand out as powerful anomalies. Places where the gravitational pull is so strong that nothing, not even light, can escape once it crosses a boundary known as the event horizon. This makes them invisible to the human eye and only detectable through their dramatic effects on the surrounding matter and light. The concept of a black hole is not just a product of modern science fiction. It is deeply rooted in our understanding of physics and dates back to Einstein's general theory of relativity, which showed how massive objects can distort the fabric of space-time itself. When a star, many times the mass of our sun, uses up its nuclear fuel, it collapses under its own gravity and forms a singularity, an infinitely small point where density and gravitational forces reach extremes we cannot fully understand. Around this singularity is the event horizon, not a physical surface, but a spherical boundary beyond which escape becomes impossible, even for light. The gravitational pull of a black hole is so powerful that it not only distorts the trajectories of nearby objects, but also bends light itself, leading to fascinating phenomena such as gravitational lensing. This effect causes the light from stars located behind a black hole to bend around the hole, sometimes forming rings of light or multiple distorted images of the same star. A true marvel of cosmic optics that has become a powerful tool for astronomers to detect and study these hidden giants. But not all black holes are the same. Some are stellar black holes, a few times the size of our sun, formed by the collapse of individual stars. Other, much larger, are known as supermassive black holes and are located at the centers of galaxies, including our Milky Way. These giants can be millions to billions of times more massive than the sun and play a crucial role in the formation and evolution of galaxies, acting like cosmic engines that propel matter and energy through vast regions of space. These mysterious cavities of gravity challenge and enrich our understanding of the fundamental laws of physics. They are natural laboratories for extreme physics, places where the forces at play challenge our established theories about how the universe works. The recent observation of gravitational waves, ripples in the fabric of space-time created by the collision of black holes, has opened up a new way for us to study these enigmatic objects. Through such observations, we gain insights into the nature of gravity, the behavior of matter under the most extreme conditions, and the structure of space-time itself. Scientific background. To truly understand the mysterious attraction of black holes, we must start with Einstein's general theory of relativity. Think of this theory as a master key, a key that unlocks the secrets of gravity, space, and time. According to Einstein, mass not only exists in space, but it deforms space-time itself. Black holes are the ultimate manifestation of this idea, regions in space where gravity is so strong that it pulls everything, even light, into an abyss from which there is no escape. These are places where our known physical laws break down and our usual concepts of time and space simply no longer work. It all starts with a massive star. When such a star uses up its nuclear fuel, the external pressure that once kept it from collapsing is no longer there to counteract its immense gravitational force. The result? The star collapses under its own weight until it forms a singularity, a point of infinite density where, frankly, everything we think we know about physics collapses. Surrounding this singularity lies the event horizon, a boundary that acts like a cosmic one-way street. Nothing that crosses it ever comes back. Beyond the event horizon, even light is helplessly exposed to the unstoppable pull of the black hole. The gravitational influence of a black hole affects not only nearby stars or stray planets, but also the nature of space-time around the whole. The force of attraction distorts the light, creating a phenomenon known as gravitational lensing. Imagine a beam of light that has traveled billions of years and then hits a black hole. Instead of disappearing, the light is bent and wrapped around the black hole, creating rings and arcs that seem almost like ghostly echoes of the distant universe. These echoes are one of the most compelling pieces of evidence for black holes, visible proof of their incredible gravitational influence. It's one of the few ways we can truly see these monstrous entities, by watching them change the universe around them. But the formation of black holes is not limited to the death of stars. The best-known mechanism is the collapse of a massive star into a black hole, but that is only one piece of the cosmic puzzle. Imagine massive gas clouds in the early universe collapsing directly into black holes without first becoming stars. Or imagine the dramatic collision of two neutron stars merging in a spectacular, violent embrace that culminates in the formation of a black hole. These processes demonstrate the versatility of nature, which is capable of creating black holes through a variety of cosmic dances. Black holes also come in many shapes and sizes. Those that have formed from collapsed stars are called stellar black holes. Although fascinating in their own right, they are overshadowed by the true giants of the universe, supermassive black holes. These colossal structures, millions or even billions of times more massive than our Sun, sit like cosmic monarchs at the centers of galaxies, dictating the movements of stars, gas, and even entire galactic structures. The Milky Way itself has one of these titans at its center, Sagittarius A, a gravitational powerhouse that plays a crucial role in the dynamics of our galaxy. These supermassive black holes are far more than cosmic curiosities. They are the architects of galaxies and influence star formation, galactic rotation, and even the fate of the universe. Studying black holes is not just about the influence of gravity or sheer mass. Black holes are extreme laboratories where we can study forces and conditions that we could never replicate on Earth. A crucial breakthrough in our understanding of black holes was the observation of gravitational waves, tears in the fabric of space-time caused by some of the most violent events in the universe, such as black hole mergers. Einstein predicted these waves over a century ago, but it wasn't until 2015 that we finally detected them, confirming that the universe itself trembles and shakes when black holes collide. These gravitational waves contain information about the black holes that created them, about their mass, their spin, and even the nature of the collision. Yet despite everything we know, black holes remain a mystery that may hold the key to understanding our origins. What if black holes are more than just stellar remnants or galactic architects? Could they be portals to other universes? What if at the heart of every black hole lies the seed of a new universe, a new Big Bang waiting to explode into existence? The singularity that constitutes a black hole is strikingly similar to the singularity that marked the beginning of our universe. Perhaps black holes are not ends, but beginnings, gateways through which matter, energy, and information are reborn, reshaped, and recycled into something entirely new. The possibility that our own universe could lie within a black hole is not just a theoretical exercise, but a revolutionary idea that forces us to rethink everything we think we know about existence and reality itself. If this is true, it would mean that our universe is part of an endless chain of universes, each emerging from the depths of a black hole, and each containing black holes that in turn give rise to further universes. This is a concept that is difficult to grasp, but which makes the study of black holes all the more important. These cosmic voids, these star graves, could actually be the womb of creation. As we continue our exploration, we must grapple with the incredible mysteries that black holes pose. They are not just anomalies to be explored, but also profound symbols of the infinite potential of the universe, places where everything we know collapses, and where perhaps everything begins anew. So join us on a journey into the shadows of black holes, beyond the limits of our knowledge, to explore the limitless possibilities hidden within these mysterious cosmic giants. Types and sizes of black holes. Black holes come in different types and sizes, each with its own properties, origin, and influence on the cosmos. Their diversity helps us understand the vast mechanisms at work in the universe and the crucial role they play in shaping everything we see, and even what we cannot see. From small stellar remnants to colossal giants at the center of galaxies, black hole types tell a story that ranges from the birth of stars to the enigmatic force that drives cosmic evolution. Stellar mass black holes are the byproducts of the dramatic and violent death throes of massive stars. When a star with at least 8 times the mass of our Sun reaches the end of its life cycle, it can no longer sustain the nuclear fusion reactions that counteract its gravitational pull. When this delicate balance breaks down, the star undergoes a massive gravitational implosion, compressing all of its matter into an infinitely small, incredibly dense point, a singularity. This singularity is the heart of the black hole, a point where the laws of physics as we know them break down. Stellar mass black holes are scattered throughout the universe and often hide in obscurity, where they can only be detected by the devastation they wreak on their surroundings. These black holes typically have a mass a few to a few dozen times that of our Sun, but don't let their comparatively small size fool you. The gravitational pull of a stellar mass black hole is sufficient to distort space-time extremely. In binary star systems where a stellar mass black hole and a companion star exist in a cosmic dance, the black hole's gravity often tears material from its partner and funnels it into an accretion disk. The stirred-up matter heats up to millions of degrees, releasing intense X-rays that can be detected over vast cosmic distances. Through this X-ray radiation, astronomers have often found evidence of stellar mass black holes, cosmic ghosts that greedily feed on their stellar neighbors. The explosive death of a massive star collapsing into a stellar black hole can also lead to gamma-ray bursts, extremely powerful bursts of energy that can overshadow entire galaxies for a few seconds. These outbursts are among the most energetic events in the universe and provide a fleeting but dazzling glimpse into the otherwise hidden processes that lead to the formation of stellar black holes. Despite their frequency, stellar mass black holes are only the smallest of the colossal structures lurking in the universe. And then there are the true giants of the universe, supermassive black holes, truly cosmic leviathans. These black holes have millions to billions of times the mass of our Sun and are located at the centers of almost all large galaxies, including our own Milky Way. The Milky Way's central black hole, Sagittarius A, is estimated to be 4 million times the mass of the Sun. But Sagittarius A is considered modestly compared to some supermassive black holes, such as the one at the center of the galaxy M87, which weighs in at an astonishing 6.5 billion times the mass of the Sun. The origins of these giants are shrouded in mystery and are the subject of ongoing debate among scientists. Did these giants arise from the direct collapse of massive primordial gas clouds in the early universe? Or did they originate from smaller black holes that gained mass by merging with other black holes and developed huge amounts of gas and dust over billions of years? These are questions that push the boundaries of our understanding of cosmic evolution. It is known that supermassive black holes exert a profound influence on their host galaxies and shape them over cosmic timescales. Supermassive black holes are not just passive spectators in the centers of galaxies. Their gravitational pull influences the orbits of billions of stars, while their activities, such as the accretion of matter, can produce energetic bursts that regulate star formation throughout the galaxy. These outbursts, often observed as high-speed jets of charged particles, can extend over hundreds of thousands of light-years and alter the structure of their host galaxies. Supermassive black holes are also thought to influence the evolution of galaxy clusters, playing a role in how galaxies assemble, merge, and change. Their presence challenges us to question everything we think we know about cosmic structures. Would galaxies even exist in their current form without supermassive black holes? Or are these giants an essential part of the formation process of the galaxies themselves? Some theories even assume that every galaxy is born around a black hole, so that these mysterious structures are the nucleus of cosmic creation and not just endpoints of destruction. Supermassive black holes are an interstellar balancing act, both creators and destroyers, that is essential to the dynamics of the universe. Then there is the strange case of medium-mass black holes. They lie in the middle between stellar and supermassive black holes and have a mass that is hundreds to thousands of times the mass of the Sun. One could consider it the missing link in the chain. Only, unlike in biology, we have not yet found many conclusive examples of it. Theoretical astrophysicists suspect that they are formed by the merger of smaller black holes or the collapse of exceptionally massive stars, but their existence remains elusive and buried in the mysteries of cosmic evolution. Why are they important? Because understanding these intermediate mass black holes could help answer one of the biggest questions about supermassive black holes. How did they get so fast and so big? If intermediate mass black holes exist, They could tell us a story of hierarchical mergers, small black holes merging to form larger ones, eventually leading to the monstrous supermassive black holes we see today. They are like cosmic stepping stones, and their discovery could help us trace the evolution of the universe's largest gravitational bodies. One possible way for the formation of medium-mass black holes is the merger of smaller black holes. Imagine a bunch of stellar mass black holes slowly drifting towards each other in the densely packed core of a star cluster, and eventually merging into a larger, more massive entity. Another possible formation scenario is the collapse of particularly massive stars, although such events are extremely rare in the current era of the universe. These black holes may have been more common in the early days of the universe, when conditions were more favorable for the direct collapse of massive gas clouds. The discovery and study of intermediate black holes could provide crucial insights into the formation of supermassive black holes. If these elusive intermediate black holes do indeed exist in large numbers, they could be the missing link that explains how supermassive black holes were able to grow so quickly in the early universe, and bridge the gap between the small and the colossal. Observations are still sparse, but astronomers are on the lookout, using sophisticated techniques such as gravitational wave detection and high-resolution X-ray observations to find these potential cosmic waypoints. Primordial black holes are a theoretical class of black holes that may have been formed not by the death of stars, but in the chaotic and turbulent moments after the Big Bang. In those early moments, when the universe was still an incredibly hot, dense soup of particles, tiny fluctuations in density could have led to the formation of black holes. These black holes, formed from the raw material of the Big Bang itself, could have masses ranging from subatomic orders of magnitude to many times the mass of the Sun. Unlike other black holes, primordial black holes are not associated with the death of a star. They represent the fundamental forces of creation and collapse that were at work in the formation of the universe. If they exist, primordial black holes could provide explanations for some of the most puzzling questions in cosmology. For example, they are considered potential candidates for dark matter, the mysterious, invisible substance that makes up about 85% of the mass in the universe. The idea is that primordial black holes could be scattered throughout the cosmos, exerting the gravitational pull necessary to explain the observed behavior of galaxies without being visible themselves. Detecting black holes in their original state is not an easy task. Because of their potentially small size and mass, they could be virtually invisible, making themselves noticeable only through their gravitational effect, or, hypothetically, through the Hawking radiation they might emit as they gradually lose mass. Primordial black holes may also play a role in the formation of large-scale cosmic structures by acting as gravitational nuclei to help contract matter in the early universe, ultimately leading to the formation of galaxies. They are more than just relics from the distant past. They could hold the key to understanding the forces that shape the universe we live in today. From relatively small stellar holes to gigantic supermassive black holes, and the elusive intermediate and primordial black holes, they offer a glimpse into a dynamic universe marked by both creation and destruction. Each type of black hole adds a different note to the symphony of the cosmos. They are the remnants of stars, the engines of galaxies, and possibly even the echo of the birth of the universe itself. Their gravitational influence shapes the flow of matter and energy, dictates the dance of galaxies, and challenges our understanding of physics. The universe, in all its vastness and complexity, is in many ways a story of black holes. Stay with us as we continue to explore the enigmatic nature of black holes, their role in the universe, and the profound questions they raise about existence, time, and the fabric of reality. Black holes as cosmic laboratories. Black holes, with their mysterious attraction and unimaginable powers, are among the most fascinating natural laboratories for testing the limits of physics. They offer us unique opportunities to explore the behavior of matter and energy under conditions that are absolutely impossible to replicate on Earth. These are not just any experiments, they are extreme in every respect. Gravitational forces, so powerful they distort the fabric of space and time, temperatures that reach unimaginable heights, and radiation that tears the cosmos apart. In this cosmic melting pot, the rules of physics are challenged and sometimes even broken, giving us a front-row seat to the mysteries that lie at the heart of our universe. One of the most fascinating aspects of black holes is their role in testing Einstein's general theory of relativity. Black holes are, by nature, cosmic arenas in which the predictions of relativity must pass their toughest test yet. Observing the behavior of stars orbiting the supermassive black hole at the center of our Milky Way has already provided clear evidence for Einstein's work. The precision with which the theory of relativity explains the movement of these stars is truly remarkable. But we should not rejoice too soon in our complete understanding. Black holes represent such extreme scenarios that the theory of relativity reaches its limits, especially near the singularity, that mysterious core where gravity becomes infinite and all known physical laws no longer apply as we know them. Here, in this paradoxical heart of darkness, the universe challenges us to question everything we think we know. But the story doesn't end with the theory of relativity. There is another competitor in this cosmic battle: quantum mechanics, the set of rules that governs the smallest particles in our universe. The singularity at the core of a black hole is a place where quantum mechanics and general relativity collide, and frankly, they don't get along. The laws that govern the cosmos on a large scale seem incompatible with the rules that apply in the quantum realm. This is the battleground for a theory of quantum gravity, a missing piece of the puzzle that could unite the large and the small. Black holes are not only mysterious cosmic entities, but also a paradox that physicists hope will enable an even deeper understanding that reconciles these two contradictory worlds. Imagine the insights that could come from finally understanding how the smallest particles interact with the most powerful gravitational forces in the universe. This could change everything, from our understanding of the beginnings of the universe to the nature of existence itself. The recent discovery of gravitational waves, ripples in space-time produced by merging black holes, represents a revolutionary step in our ability to study these enigmatic giants. These waves are like a whisper from the universe, telling of gigantic collisions that would otherwise remain in the dark. For years, these collisions were little more than theoretical considerations. But now we can hear the echoes of the colliding black holes and feel the reverberations of their existence. These discoveries have given us a glimpse into details we once thought unimaginable, like the mass and spin of these black holes, and even the dynamic dance they perform as they orbit each other. This kind of data is invaluable. It's almost as if the universe is showing us its private notes and letting us glimpse into a hidden chapter of its great history. Black holes not only help us understand gravity and the theory of relativity, they also allow us a glimpse into the strange world of quantum phenomena under extreme conditions. Stephen Hawking once shocked the scientific community with his theory of Hawking radiation, the idea that black holes can emit radiation while slowly losing mass until they eventually dissolve into nothing. This idea was not just groundbreaking. Hawking radiation shows that black holes are not eternal. They live, they lose mass, and at some point they may even die. This has far-reaching consequences. If black holes can evaporate, what happens to all the information about the matter they have swallowed? This is the infamous information paradox that puzzles some of the world's brightest minds. Could it be that the universe is not protecting information as we thought? Could black holes be loopholes in the cosmos where information simply ceases to exist? Or is there something deeper, something we haven't yet understood? Another limit lies in the high-energy environments that create black holes. When matter is drawn by the immense gravitational pull of a black hole, it forms an accretion disk, a spiraling, chaotic disk of gas and dust heated to extreme temperatures. This disk not only glows, it radiates across the entire electromagnetic spectrum, from radio waves to X-rays. Observing this radiation is like reading the fingerprints of a black hole. They tell us about the powerful processes taking place there, about the incredible acceleration of particles, and about the incredible mechanisms that power some of the brightest objects in the universe, such as quasars. The more we learn, the more we realize that black holes don't just swallow matter. They are powerhouses that shape galaxies and influence cosmic evolution. Despite their fearsome reputation, black holes are essential to our understanding of the universe. They challenge us to rethink the laws of physics and inspire us to explore the deepest, darkest corners of our cosmic neighborhood. They hold secrets about the nature of gravity, the fate of information, and perhaps even the birth and death of universes. They force us to grapple with questions that are as profound as they are difficult. What happens to time and space when they are bent to the point of breaking? What really lies beyond the event horizon? When we study black holes, we are not just exploring distant points in the cosmos, we are exploring the structure of reality itself. Stay with us as we continue this journey through the cosmos. Black holes are more than just celestial mysteries. They are the universe's own laboratories, pushing our understanding to the limits and maybe, just maybe, giving us a glimpse of what lies beyond. Formation and evolution. Black holes are formed by some of the most dramatic and violent events in the cosmos, and their growth and evolution are a testament to the most extreme forces in the universe. They are the ultimate transformers of the universe, consuming and redistributing matter and energy in a relentless cycle that shapes galaxies and drives cosmic evolution. Understanding how black holes form and evolve isn't just about understanding a phenomenon. It's about deciphering the dynamics that govern the cosmos. The most common way for black holes to form begins with the death of massive stars. These colossal stars, many times larger than our Sun, spend millions of years balancing the outward pressure of nuclear fusion against the relentless inward pull of gravity. This delicate balance is temporary and is maintained only as long as the star has enough nuclear fuel to burn. When this fuel is used up, the balance is thrown out of whack. Gravity takes control, and the core of the star collapses in a massive implosion. For stars that exceed a certain mass, this collapse is so extreme that it forms a singularity, a point with infinite density and zero volume. This is how a black hole is born. But the story doesn't end there. The death of such a massive star often results in a supernova, a cosmic detonation that briefly overshadows an entire galaxy, releasing huge amounts of energy and scattering heavy elements into space. These supernovae are not only spectacular, but also crucial for the formation of new stars and planets that supply the universe with the building blocks of life. What remains after the explosion is either a neutron star or, if the original star was massive enough, a black hole. These stellar black holes are scattered throughout the universe and often form binary star systems. During these pairings, the black hole can begin sucking material from its companion star, creating a swirling accretion disk and releasing some of the most energetic emissions seen in the universe, X-rays and gamma rays that shine through space like cosmic beacons. The formation of supermassive black holes, cosmic giants with millions to billions of times the mass of our Sun, is one of the most exciting mysteries of modern astrophysics. Unlike their smaller counterparts, these giants cannot be explained by the collapse of a single star. Instead, their formation probably began in the early universe, where primordial gas clouds collapsed directly into black holes, bypassing the stellar phase entirely. These early seeds then grew through a process of merging and relentless consumption, absorbing smaller black holes and feeding on gas, dust, and stars for billions of years. Supermassive black holes are found at the heart of most galaxies, including our own Milky Way, where one is hidden behind clouds of gas and dust, Sagittarius A. These giants play an important role in galactic evolution and act like cosmic engines. As they feed, they emit enormous jets of radiation and particles that eject matter at nearly the speed of light, sometimes preventing entire regions of a galaxy from forming new stars. It sounds counterintuitive, but these supermassive black holes are not only destructive forces, they also regulate growth and ensure that galaxies evolve in a balanced manner. Too much star formation would destabilize a galaxy, and supermassive black holes help prevent this, maintaining a cosmic harmony that is as brutal as it is beautiful. Another fascinating chapter in the history of black hole evolution is the phenomenon of mergers. Black holes do not exist in isolation. The galaxies themselves are in constant interaction, merging and colliding. When two galaxies merge, their central black holes are drawn together in a cosmic ballet, spiraling toward each other while radiating gravitational energy. This process, which can take millions of years, culminates in a catastrophic merger, a collision so powerful that it sends ripples through the fabric of space-time. These waves, called gravitational waves, were first discovered in 2015. They are direct evidence of black hole merging and confirm important predictions of Einstein's general theory of relativity. The energy released during these mergers is unimaginable and, for a brief moment, exceeds the luminosity of all the stars in the observable universe. These mergers are more than just a spectacular spectacle. They provide crucial insights into the nature of black holes, their populations, and the dynamics of our universe. Observatories like LIGO and Virgo have allowed us to listen to the cosmos, hear the final death sounds of merging black holes, and understand the universe in a new way. It's almost ironic. Objects so dark they don't let any light through are among the loudest voices in the cosmos, their mergers echoing across billions of light years. Accretion is one of the main ways black holes grow, and it is a process that reveals both the monstrous appetite and the creative power of these objects. Matter pulled towards a black hole does not simply disappear. Before it crosses the event horizon, it collects in an accretion disk, a swirling vortex of gas, dust, and sometimes entire stars that are torn apart by tidal forces. The friction in this disk generates enormous heat, which causes it to emit radiation across the entire electromagnetic spectrum. This radiation makes black holes indirectly visible and turns them into some of the brightest objects in the universe. Quasars, the ultra-bright centers of some distant galaxies, are powered by supermassive black holes that devour matter at incredible speeds. These cosmic lighthouses can dwarf their entire host galaxy and are visible across billions of light years. But there's a paradox here. These extraordinarily luminous objects are powered by something that is itself a void, a gravitational abyss that lets nothing through once it crosses a certain threshold. This juxtaposition, the brightest lights are driven by the darkest shadows, is what makes black holes so fascinating. But one should not believe that black holes are insatiable monsters that devour everything in their path. Most of the time, black holes are inactive and sit quietly in the darkness. They only become active when a star comes too close to them, or when galaxies collide and feed them new material. The act of accretion is rare and precious, a fleeting event in the lifetime of a black hole, but one that has profound consequences for the universe. The formation and evolution of black holes is fundamental to understanding the universe. From the death throes of massive stars to the silent but unstoppable growth of supermassive black holes at the centers of galaxies, black holes are not just passive remnants, they are dynamic actors in shaping the cosmos. They regulate star formation, distribute heavy elements, and even shape the structure of galaxies. Black holes stand at the intersection of creation and destruction, reminding us that these two forces are inextricably linked in the universe. The further we delve into the mysteries of black holes, the more we realize that they are more than just the ultimate void. They are the key to understanding the fundamental laws of nature, to understanding how everything we see came to be, and how it might one day end. Stay with us as we unlock more mysteries and delve into the deepest shadows to discover the building blocks of our universe. Characteristics of black holes. Black holes are paradoxical in nature, seemingly simple, yet so complex that they have puzzled scientists for decades. These cosmic puzzles have a few crucial properties that determine their behavior and influence the universe. Understanding their mass, spin, and charge is the key to unlocking the mysteries that surround them. But behind these seemingly simple properties lie fascinating nuances that redefine our understanding of the universe and the nature of existence. The mass of a black hole is not just a number. It is the source of its power, the essence that determines its gravitational pull. Mass determines the size of the event horizon, the invisible, unyielding boundary that marks the point beyond which nothing can escape. The greater the mass, the larger the event horizon, and thus the gravity, which not even light can overcome. This strong gravitational pull determines the fate of stars, gas clouds, and entire solar systems that are too close to it. The gravitational influence of black holes extends far beyond their event horizon, shaping the orbits of nearby stars and curving the structure of space. Mass makes a black hole the ultimate cosmic gatekeeper. Anything that crosses the boundary is lost forever. This creates an eerie sense of finality that defies our instinctive understanding of the universe. But now things get interesting. This seemingly endless attraction of the masses raises questions. What if black holes aren't just cosmic garbage dumps for dying stars? What if they hold the key to understanding the most fundamental aspects of reality? Finally, black holes with masses ranging from a few times that of our Sun to billions of solar masses can either devour a lone star or dominate an entire galaxy. Their mass is more than just a property. It is a force of cosmic destiny, the silent architect of order and chaos in the universe. Spin is the hidden dynamo of a black hole, a feature that further increases its complexity. Black holes are not just static voids. They are active, dynamic, and incredibly powerful entities that spin at astonishing speeds. Some black holes rotate at a speed close to the speed of light. Imagine the consequences of such rapid rotation. The fabric of space-time is twisted and dragged along, a phenomenon physicists call frame dragging. It is as if the black hole is disrupting the universe, changing everything around it and bending not only space but also time itself. This rotation affects the accretion disk, a swirling inferno of gas and debris spiraling towards its demise. The faster a black hole spins, the more energy it can extract from this disk and create powerful relativistic jets that shoot particles into space at almost the speed of light. These jets can be seen from millions of light years away, and serve as cosmic beacons that tell us where these monsters are. The spin of a black hole explains its history in many ways. Did it arise from the collapse of a single star, or did it evolve through countless mergers and cosmic collisions? The faster it spins, the more dramatic its story. A story of catastrophic growth and insatiable hunger. But perhaps the spin is more than just a relic of its past. Perhaps it plays a central role in a larger cosmic mechanism. Could the high-speed rotation of black holes serve as a counterbalance and prevent the universe from descending into entropy? Or perhaps it is just a relentless reminder that once energy is set in motion, it cannot be stopped so easily. In any case, rotation is what gives black holes their restless energy, a force that shapes galaxies and influences cosmic evolution in ways we are only beginning to understand. The concept of charge is perhaps the most mysterious and least understood property of black holes. While mass and spin have been extensively studied, the idea that a black hole could have an electrical charge takes us into speculative territory. Theoretically, black holes can have an electrical charge, but most observed black holes are considered electrically neutral. The reason for this is simple. Any imbalance in charge would be quickly neutralized, because the black hole attracts oppositely charged particles. Nevertheless, the possibility of a charged black hole is more than an academic curiosity. It forces us to question our knowledge of these enigmatic objects. What if there are rare cases where charge plays an important role and exotic types of black holes emerge that behave differently than the ones we know? Perhaps there are anomalies out there, charged black holes that can interact with the universe in unique ways, creating magnetic fields beyond our current understanding. The existence of such black holes could open up entirely new avenues of research and close the gaps between Einstein's equations and quantum mechanics. The possibility of charged black holes forces us to consider the limits of our theories and challenges us to look deeper and question more. At the core of every black hole lies the singularity, a point where density becomes infinite and the known laws of physics collapse into incomprehensibility. The singularity is the point where all the mass of a black hole is concentrated and where space and time cease to exist as we understand them. This is not just a theoretical point, but the embodiment of the limits of our current science. Our understanding, based on general relativity, collapses completely in the face of such extreme conditions. The singularity is both a mystery and a promise. A mystery because we cannot yet understand what is happening within it, and a promise because it points to deeper truths about the universe. Truths waiting to be discovered. What happens when physics itself fails? The singularity is a challenge for science, a cosmic test of courage that asks us to rethink everything we know. It reminds us that our theories are incomplete and that there are places in the universe where our understanding simply does not apply. The quest to understand the singularity is, at its core, the quest to unify quantum mechanics and general relativity, a goal that could fundamentally change our perception of reality. Until we understand the singularity, we have to come to terms with the uncomfortable idea that there are places in the universe where the rules we live by simply do not apply. The event horizon is probably the most well-known feature of a black hole, the boundary that separates the known universe from the great unknown. It is not a physical surface, but an invisible veil which, once crossed, seals the fate of all who dare to come too close to it. It is the ultimate one-way street. Nothing can return, not even light, once it crosses this threshold. The event horizon is the boundary between the comprehensible universe and the abyss, a place where our physical laws still apply, but only just. The size of the event horizon depends directly on the mass of the black hole, and it is this boundary that gives black holes their name, an object so dense and whose gravity is so strong that it swallows even light itself. But beyond this border lies the ultimate mystery. What secrets lie beyond the event horizon? What fate awaits the stars, planets, and particles that pass through it? In a sense, the event horizon is more than just a boundary. It is a challenge to our curiosity. He invites us to reflect on what it means to know, to understand, and to explore. It is a cosmic invitation we cannot resist, even if the price of crossing the border is the loss of all information, forever. Studying the properties of black holes, mass, spin, charge, and the nature of the singularity provides valuable insights into their behavior and their influence on the surrounding cosmos. These properties determine how black holes interact with matter, how they grow, and how they influence the evolution of galaxies and larger cosmic structures. Understanding these features helps scientists understand the role of black holes shaping in the universe and deepens our understanding of the fundamental laws of nature. Stay tuned as we explore the wild extremes of black holes, their impact on the birth and death of stars, the mysteries of their jets, and the tantalizing notion that they might even hold the secrets of the beginning of the universe itself. The journey has only just begun, and the deeper we go, the more exciting the discoveries become. Groundbreaking discoveries. The study of black holes is at the forefront of modern astrophysics. Recent breakthroughs are pushing the boundaries of our understanding of these mysterious objects. These discoveries not only deepen our knowledge, but also challenge our understanding of the fundamental laws of physics and ask us to rethink some of our deepest assumptions about the universe. One of the most compelling concepts in black hole physics is Hawking radiation. In the 1970s, Stephen Hawking proposed that black holes are not completely black, but can emit radiation due to quantum effects near the event horizon. This groundbreaking theory contradicted the traditional idea of black holes as insatiable cavities that swallow everything, including light, and are never seen again. Instead, Hawking suggested that black holes might, paradoxically, be able to radiate energy. This radiation is caused by quantum fluctuations at the event horizon, where pairs of particles spontaneously form and annihilate. Occasionally, one particle falls into the black hole while the other escapes, resulting in a net loss of mass from the black hole. Over an unimaginably long period of time, this process could cause a black hole to completely evaporate, a cosmic escape attempt that is as fascinating as it is disturbing. The effects of Hawking radiation are profound. It bridges the gap between quantum mechanics and general relativity, two pillars of modern physics that often seem incompatible. Hawking's idea suggests that black holes could eventually disappear, leaving behind a question that continues to preoccupy physicists. What happens to the information they contain? Does it disappear forever, thus violating the principles of quantum theory? Or does it persist in a way we have not yet understood? This debate remains one of the most controversial and exciting in theoretical physics. The focus is on Hawking radiation, a glimmer of hope that the mysteries of quantum gravity could one day be solved. Hawking radiation also raises disturbing questions about the fate of the universe itself. If black holes can really evaporate, could this process play a role in the ultimate end of the universe? Some speculate that black holes may slowly shrink and disappear in the distant future, contributing to a cold, dark cosmos in which all the stars have burned out, a universe that gradually dissolves into nothingness. A frightening thought that leads scientists to search for the missing pieces of this cosmic puzzle. In 2019, the Event Horizon Telescope, EHT, gave the world one of the most famous images in modern science, the shadow of a black hole. This image, taken at the heart of the galaxy M87, was not only a scientific triumph, but also a profound insight into the dark and mysterious forces that shape our universe. The sight of the glowing ring of light, the bright accretion disk swirling around a seemingly empty void, provided visual confirmation of a phenomenon that for a long time existed only in the abstract realm of equations and theories. The achievement of the EHT was monumental, not only because it confirmed the existence of a black hole, but also because it brought together scientists, data, and technology from around the world. By creating a virtual Earth-sized telescope, the EHT was able to peer into the boundaries of known physics and capture details that had eluded us for decades. This milestone has paved the way for even more ambitious projects. We may soon catch a glimpse of the black hole at the center of our own galaxy, Sagittarius A, a silent, shadowy colossus lurking at the heart of the Milky Way. Direct observation of black holes gives us more than just images. It offers the opportunity to test the limits of Einstein's general theory of relativity in the extreme environments these objects create. If discrepancies arise between observation and theory, the results could force us to rethink our understanding of space and time. For example, imagine we found something that contradicted general relativity. What then? This could usher in a scientific revolution comparable to the discoveries of Copernicus or Newton, fundamentally changing our perception of reality. The success of the EHT also highlights an important aspect of black hole science: collaboration. The sheer magnitude of this feat, which requires coordination between observatories around the world, reminds us that exploring the deepest mysteries of the universe is not a solitary endeavor. It is a collective effort that transcends boundaries and unites humanity in the quest to understand our place in the cosmos. In 2015, a wave went through the universe, not just metaphorically, but literally. The Laser Interferometer Gravitational Wave Observatory, LIGO, detected gravitational waves for the first time, a discovery that would revolutionize our understanding of the cosmos. These waves, caused by the merger of black holes 2 billion light-years away, provided direct evidence that black holes are not isolated, solitary objects, but dynamic entities capable of colossal, energetic interactions. The discovery of these gravitational waves confirmed what was once only a theoretical prediction by Einstein. Space and time can ripple, bend, and stretch under the influence of cataclysmic events. Since that first discovery, LIGO, in collaboration with Virgo and Kagra, has recorded dozens of gravitational wave events, many of which involve black holes merging in a cosmic dance of unimaginable scale. Each discovery reveals a little more about these elusive objects, how they form, how they rotate, and how they interact. With each wave that passes Earth, we gather more evidence that helps fill in the gaps in the evolution of black holes. Gravitational wave astronomy is still in its infancy, but it has already opened up a new perspective in astrophysics. Unlike light, gravitational waves penetrate matter almost undisturbed and allow us to look into regions of the universe that are otherwise completely darkened. They allow us to listen to the universe, a cosmic symphony made up of the collisions of black holes, neutron stars, and perhaps one day even more exotic phenomena we have yet to imagine. The significance of gravitational waves goes beyond black holes. They provide insights into the fabric of space-time itself and allow us to study events that would otherwise leave no visible trace. Imagine being able to feel the universe shaking as two giant black holes collide, releasing more energy in a fraction of a second than all the stars in the observable universe combined. An overwhelming thought that hints at the raw, untamed power that lurks in the cosmos. Black holes are not only an astrophysical curiosity, but also a crucible for some of the most exciting questions in modern physics. The singularity at the center of a black hole is a place where the known laws of physics completely fail, a point of infinite density where the equations of general relativity break down. To understand what happens in such a place, we need something beyond Einstein's theory of relativity. We need a theory that can bridge the gap between the large and the small, between stars and subatomic particles, a theory of quantum gravity. There are several theories that could explain this. String theory, which states that all particles are one-dimensional strings vibrating at different frequencies, is one of the contenders. Loop quantum gravity, which assumes that space-time itself is quantized, is another. Although both approaches are fundamentally different, they attempt to achieve what physicists have failed to do for over a century, to unite the theories of the very large and the very small. Black holes are the perfect natural laboratories to test these ideas. If we could understand how quantum mechanics and gravity interact inside a black hole, we could unlock the key to understanding the nature of all matter, energy, and the fabric of space-time itself. The study of quantum gravity is not just about black holes, but also about the search for a unified understanding of the universe. The singularity at the core of a black hole is like a blinking red light, signaling that our current understanding is incomplete. If we solve the mysteries of black holes, we may find answers that apply to everything from the creation of the universe during the Big Bang to the fundamental forces that govern the interactions between particles. This search is one of the great unfinished adventures of modern science, a search that could lead to a theory of everything. These groundbreaking discoveries are more than isolated scientific advances. They are stepping stones on a journey to answer questions that redefine our place in the universe. Are black holes the final state of collapsing matter, or do they contain pathways to other realms of existence? Can they tell us what happened at the beginning of time, or reveal the ultimate fate of the cosmos? When we study black holes, we not only peer into the depths of the universe, but also into the depths of reality itself, challenging our ideas about existence, causality, and the laws that underlie everything. The story of black holes is still being written. With each new discovery, the mystery deepens, and the cosmos invites us to delve further into its darkest secrets. Let's continue this journey, a journey that could ultimately change not only our understanding of black holes, but also of the universe itself, and perhaps even our place in it. Theoretical speculations. The study of black holes has not only deepened our understanding of the universe, but has also produced a wealth of theoretical speculations that expand the boundaries of what is possible. These ideas push us beyond the conventional and invite us to consider whether black holes are far more than cosmic anomalies. They could be the gateways to other worlds, or perhaps even the architects of the existence we experience. One of the most intriguing ideas is that black holes could be gateways to other universes, suggesting that they could be much more dynamic than just the endpoints of matter. Think of a black hole not as a dead end, but as a bridge to places where entirely different physical rules might apply. This concept has its roots in the theory of wormholes, hypothetical tunnels that could connect different regions of space-time. Some physicists suggest that the singularity at the center of a black hole could serve as a passageway leading to a completely different point in space-time, or perhaps even to a completely different universe. Although this theory is speculative, it resonates widely in the scientific community and forces us to rethink our understanding of the structure of existence. If true, it would mean that black holes do not simply swallow everything that crosses their event horizon, but that they offer an escape route, perhaps into something entirely new. This is directly related to the tantalizing concept of the multiverse. Imagine a scenario in which every black hole in our universe serves as the starting point for a new universe, a branching off, a seeding of existence. When matter collapses into a black hole, it may not simply disappear into the void, but become the basis of a young universe, a baby universe that grows and evolves on its own. Think of our universe not as a singular, unique event, but as one of an infinite family of universes, each with its own physical laws, possibilities, and even versions of reality. And there are no observations yet to prove this. It is a vision that challenges the limits of our scientific knowledge and reminds us that we may just be inhabitants of a cosmic bubble in an unfathomably vast cosmic froth. This concept forces us to rethink our idea of black holes as purely destructive forces. Instead, they could be gateways to birth, portals through which entirely new universes emerge, transcending the boundaries of our understanding. What if the creation of a black hole is not an end, but a beginning, a cosmic birth that carries within it the seed of another reality? Every star that collapses under its own weight could set the stage for a new cosmic story, one that unfolds in a universe far removed from our own. The mysterious singularity, this point of infinite density, could be the womb of an entirely different world, where physics as we know it bends, twists, and transforms into something we could never have imagined. This thought is both frightening and exciting, because if it is true, black holes are not just cosmic tombstones marking the death of stars, but also beacons of creation, heralding the arrival of new worlds and new possibilities. Another intriguing speculation is the idea that our entire universe could exist inside a black hole. It sounds almost paradoxical, but when you look at the similarities between the mathematical descriptions of black holes and the conditions of the Big Bang, the picture takes shape. In both cases, we are dealing with singularities, infinitely dense points where the known laws of physics break down and space-time as we know it ceases to behave predictably. Some physicists even suspect that the universe we observe is the interior of a black hole located in a much larger mother universe. In this scenario, the event horizon, the boundary from which nothing can escape, could correspond to the observable boundary of our universe. Everything we know, from galaxies billions of light years away to the tiniest particles under our microscopes, could be contained within an all-encompassing black hole that represents only a tiny part of a larger reality. Life inside a black hole has profound implications for our understanding of space, time, and even our very existence. The extreme curvature of space-time inside a black hole could explain some of the most puzzling properties of our universe. Its apparent flatness, the delicate balance that allows life to exist, and the rapid expansion that scientists attribute to the mysterious power of dark energy. What if the reason our universe is expanding is because the black hole we are in is still growing and still attracting matter and energy from the larger universe outside? What if the relentless gravitational pull that defines a black hole is precisely the force driving the expansion of everything we know, an inevitable process unfolding within a colossal cosmic machine? These kinds of questions provoke discussion and sometimes discomfort because they force us to confront the possibility that our entire existence is just a small part of a much larger cosmic mechanism. A mechanism that we are just beginning to understand. Black holes could be not only destructive endpoints, but also creative hubs of unimaginable complexity. What if, in the grand scheme of things, we are simply riding the currents of space-time in a colossal galactic entity shaped by forces that are both infinitely destructive and infinitely creative? These speculations may not yet be empirically proven, but they provide a framework that invites us to reconsider our position in the cosmos, not as isolated observers, but as an integral part of a much larger, possibly infinite sequence of realities. But to be clear, these ideas are often dismissed by more conservative voices in the scientific community as unprovable speculation. But isn't it precisely the nature of science to ask questions that contradict the norm and to explore the limits of what is possible, even if those limits are obscure? The truth is that we still know so little about black holes and their role in the cosmos. They could be destroyers, yes, but they could also be creators, shapers of galaxies and universes, perhaps even cradles for new beginnings. The deeper we delve into these mysteries, the clearer it becomes that black holes may contain the answers to questions we have not yet learned to ask. They may not just be cosmic vacuum cleaners that suck up everything in their path, but they could be the engines of creation that give rise to new forms of existence. The more we learn about black holes, the more we are drawn into a deeper understanding of the universe and our place in it. It's a journey where every answer only raises more questions, an invitation to look into the void and wonder what lies beyond. The multiverse theory. The multiverse theory is one of the most provocative ideas in modern cosmology, a theory that seems to push the boundaries of our imagination and challenge our understanding of existence. At its core, it states that our universe is just one of countless universes, a vast, sprawling collection of alternate realities, each with its own physical laws, fundamental constants, and even different timelines. Imagine the universe not as a single entity, but as a bubble floating among countless others, each bubble a separate, self-contained reality in which everything that could happen has already happened, is happening, or will happen. Black holes, those mysterious cavities that seem to defy all known laws of physics, could hold the secret of the multiverse. According to some theoretical models, every black hole could be the seed of a new universe. When a black hole forms, matter collapses into a tiny point, the singularity. The sheer gravity and density of the singularity could theoretically pierce our own cosmic fabric and lead to the birth of an entirely new universe beyond the event horizon. This means that every black hole could be not only an end, but also a beginning, a transition point to something beyond our reach and understanding, a new universe, unconnected to our own, but nevertheless tightly woven into the tapestry of the multiverse. This provocative concept suggests that our universe itself could be the offspring of an ancient black hole, a cosmic child born from the singularity of another universe. Perhaps the space-time fabric we live in is the result of a black hole collapsing from a completely different reality, a reality that went its own way, with its own stars, galaxies, and fundamental truths. This idea makes the boundaries of our existence seem less like final edges, but more like thresholds to other realities that blur the lines between what we understand as beginning and end. The fascinating and admittedly disturbing thing about the multiverse theory is that it challenges our most basic beliefs. Are we really alone in this universe? Or are we just a tiny part of an incredibly large cosmic architecture? If black holes are indeed gateways to other universes, this could mean that the cosmos is not a single, isolated entity, but part of a vast network of universes, each of which influences and gives rise to new ones. Every black hole we observe, every cosmic anomaly we puzzle over, could be the gateway through which an entire universe exists. A universe fundamentally different from ours or eerily similar, with subtle changes that make all the difference. The implications are both tantalizing and disturbing. If these multiverse models are true, it means that our understanding of reality is incomplete at best and hopelessly naive at worst. It forces us to confront the possibility that our universe, with all its complexity and beauty, is just one example in an infinite sea of possibilities. Maybe somewhere out there, in another universe created by a black hole, there is another version of Earth, another version of you, living under completely different physical laws and circumstances. Some physicists argue that the concept of the multiverse is an elegant escape from the difficult questions we still cannot answer about our universe. Why does our universe have exactly the conditions that allow the existence of life? Is the multiverse just a convenient way to circumvent the need for a finely tuned universe by being just one of countless ways in which life can arise? Think about it. If our universe is just one among many, perhaps our struggles, our successes, our very existence have less cosmic significance. Or maybe, just maybe, they have more meaning. Because if we are truly part of an interconnected system of realities, then everything we do could have an echo and consequences far beyond the boundaries of our universe. The birth of a black hole here could mean the birth of a new universe elsewhere, where the rules of existence are rewritten and new realities are created. Ultimately, multiverse theory isn't just about black holes or alternate realities. It's about redefining what we think is possible. It challenges us to rethink the limits of existence and to consider that our universe could be part of something much larger, something infinitely complex and beautiful that is beyond our control. If black holes are indeed cosmic gateways, then perhaps they are telling us something essential, that the end is not final, that destruction is merely a prelude to creation, and that every horizon we see is merely the edge of an undiscovered frontier. And as we peer into the depths of the cosmos, we realize that our universe may be just one chapter in a much larger story, one we are only just beginning to understand. Time dilation and reality. Inside a black hole. The extreme gravitational forces near a black hole lead to a phenomenon known as time dilation. Time itself is stretched and bent, changing the nature of reality. In the presence of such overwhelming gravity, time slows down as if it were being pulled and held hostage by the immense power of the black hole. From the perspective of an outside observer, an object falling into the black hole appears to move in slow motion, approaching the event horizon but never completely crossing it, remaining in an almost eternal moment. This is not mere speculation, but the bizarre but inescapable conclusion of Einstein's general theory of relativity. However, the reality for the object itself looks quite different. For the one falling, time flows as always. Seconds become minutes, minutes become hours, and finally they reach the singularity at the heart of the black hole, where time and space as we know, they no longer have any meaning. Consider what this means for the experience of reality in a black hole. Imagine that every moment is stretched, that the concept of future and past blurs, and that time is more like a vast ocean of possibilities than a one-way river. The effects of time dilation would be so extreme that they would contradict our usual ideas about existence. Those within the event horizon experience what seems like an eternity, while in the rest of the universe, only minutes pass, a juxtaposition that has countless unsettling implications. What would it be like to live in a place where the clockwork of the cosmos is so fundamentally disrupted, where every moment passes as if time itself were struggling to move forward? Inside a black hole, the ordinary laws of the universe dissolve, and what remains is something we can barely understand, a realm where reality itself seems to twist and fold in ways our minds can barely fathom. In truth, the thought of it is almost insane. If you fall into a supermassive black hole lurking at the center of galaxies, you might survive the first trip beyond the event horizon, but only maybe. The enormous size of these black holes means that the tidal forces are weaker at the horizon, so you could cross the horizon without immediate destruction. But make no mistake, this would not be a peaceful transition. The deeper you go, the stronger the forces of gravity become, distorting not only time but also space itself. Above becomes below, inside becomes outside. Direction loses all meaning. It's as if the universe is actively working against your mind, overturning every rule that has ever defined reality. And that is perhaps the most frightening aspect. Inside a black hole, you not only witness a new reality, but you are part of it, a fragment of an incomprehensible truth. But perhaps the strangest idea is that time inside a black hole is not bound by any limits. Could it be that in a black hole all moments, past, present, and future, exist simultaneously? In this timeless environment, you might witness the entire history of the universe unfolding, not sequentially, but all at once, as a single unbroken continuum. Some theorists even claim that the singularity at the center of a black hole is not an end, but a beginning. The seed of a new universe in which time flows differently, in which physics rewrites itself, and reality finds a way to be reborn. It is a captivating, almost poetic idea that black holes, these harbingers of destruction, could also be cradles of creation, rewriting the laws of existence in ways we are only just beginning to understand. Of course, these are just theories, fantastic, breathtaking speculations that push the boundaries of what we know about the universe. And maybe that's exactly what we need. Because black holes not only test our technology and our physics, but also our imagination. They force us to confront the uncomfortable truth that the universe may be stranger and more complex than we will ever fully understand. But that's exactly what makes the search for them worthwhile. Whether they are gateways to other universes, creators of new realities, or simply cosmic puzzles that hold the secrets of time and space, black holes are a frontier we cannot resist. The puzzles they pose inspire us to keep questioning, keep searching, and keep believing that the answers are out there. If only we have the courage to venture close enough to find them. So as we turn our eyes to the heavens again and continue our quest to understand these cosmic giants, one question remains: are we truly ready for the answers we might find? For the truth that could redefine our place in the universe? Whatever the case, one thing is certain: our journey into the unknown has only just begun. Groundbreaking discoveries. Recent technological advances have allowed scientists to gain unprecedented insights into black holes and shed light on mysteries that were once confined to the realm of science fiction. In 2019, the Event Horizon Telescope, EHT, achieved a monumental breakthrough by taking the first image of a black hole's event horizon. It wasn't just an image, but a glimpse of the edge of the unknown, a shadow against infinity, revealing the true form of gravity in its most extreme form. The EHT, a global network of radio telescopes synchronized across continents, became an Earth-sized observatory and allowed humanity to peer into the supermassive black hole at the heart of the M87 galaxy, 55 million light-years away. For the first time, we looked into the abyss, and it looked back, thus confirming, beyond theoretical considerations, that black holes are not just the stuff of speculation, but undeniable components of our universe. This was a crucial moment, but only one piece of the puzzle. Before we could catch our breath, another revelation shook our understanding of the cosmos. In 2015, the Laser Interferometer Gravitational Wave Observatory, LIGO, discovered gravitational waves, tears in the fabric of space-time itself. These waves were the echo of a cosmic catastrophe. Two black holes, spiraling together, merged and released a massive burst of energy that spread throughout the universe and eventually reached Earth billions of years later. This was the first direct evidence that black holes do not exist in isolation. They dance, collide, and reshape the structure of reality itself. This opened a new door in astrophysics. Suddenly, we were no longer just seeing the universe, but listening to it, hearing the whispers of collisions and cosmic dramas that had previously remained hidden from us. Gravitational waves became a tool to map the invisible and reveal events so distant and hidden that they might as well have been invisible. These breakthroughs have shaken the foundations of physics. Stephen Hawking's prediction of Hawking radiation continues to provoke and challenge our understanding of the universe. According to Hawking, black holes are not eternal prisons. There is a slow escape of energy, a kind of cosmic exhalation that could cause black holes to evaporate over dizzying amounts of time. Imagine what this means. The strongest gravitational forces in existence quietly dissipate and make way for the relentless course of quantum mechanics. Although we have not yet observed this radiation, the effects are already profound. Hawking radiation is more than a theory. It is a gauntlet thrown down to physics, challenging us to reconcile the quantum world with the cosmic world. It reminds us that the universe does not play by our rules. It is huge, indifferent, and infinitely complicated, and surprises us again and again. But not all scientists share this opinion. Some believe that the universe holds even deeper secrets than we can imagine, that the behavior of black holes could lead us to revelations about the true nature of reality, and possibly even reveal the flaws in our most cherished theories. Could Hawking radiation be the missing link between the smooth curves of relativity and the erratic unpredictability of quantum mechanics? Or is it just the beginning of an even greater mystery? Every discovery seems to bring with it a deeper level of complexity that challenges the established order, triggers discussions, and makes us think outside our comfort zone. And this is precisely where the true fascination lies: the questions without answers, the theories that trigger endless debates. What if the mysteries of black holes point to something even more fundamental about the structure of existence? What if in the depths of these dark monsters we find not only cosmic destruction, but also the key to understanding the birth of everything? The beginning and end of time, space, and reality itself? Some might say that we are venturing into areas we shouldn't, that we are poking into the deepest secrets of the universe and risking consequences we cannot even begin to understand. But maybe that's exactly why we have to keep going. To shy away from these questions would be to admit defeat and accept ignorance, even though the answers are within reach. And then there is the tempting idea of black holes as portals. Could they be more than just cosmic endpoints? Some theorists speculate that black holes could be gateways to other universes, or perhaps even the birthplace of new universes. Imagine a scenario in which every black hole is not a dead end, but a cosmic seed, a singularity from which a new universe is born. This astonishing idea is related to the concept of the multiverse, a collection of parallel universes, each with its own physical laws. If black holes are indeed connected to other realms of existence, it would mean that in every galaxy lies not only a point of no return, but also a potential gateway to a completely different cosmos. The implications are breathtaking, suggesting that our universe may be part of a far larger, interconnected structure, a cosmic web of realities, each influencing the others in ways we are only just beginning to imagine. These groundbreaking discoveries have not only expanded our knowledge of black holes, but have also transformed them into cosmic laboratories, places where the rules of the universe are stretched to their absolute limits. They challenge us to question everything we know about space, time, and existence itself. The journey is far from over. With each new observation, we delve deeper into the mystery of black holes, uncovering layers that both puzzle and inspire us. What secrets do they hold about the structure of reality? What do they reveal about our place in this vast, indifferent universe? Stay with us as we explore the mysterious effects of black holes on galaxies, their intertwining with quantum mechanics, and the disturbing questions they pose about the universe and ourselves. The story of black holes isn't just about science. It's about our insatiable curiosity, our desire to understand, and our place in a universe far stranger than we ever imagined. Cosmic implications. Black holes are not just isolated regions of high gravity, they are much more important. They are the architects of the cosmic fabric that extends across the entire universe. They determine the fate of galaxies, influence the formation of stars, and drive the evolution of the universe in ways we are only just beginning to understand. At the center of almost every galaxy, including our own Milky Way, lurks a supermassive black hole, a gravitational giant that exerts extraordinary influence on its surroundings and controls the behavior of entire star systems. These colossal entities do not simply exist. They are active players in the grand cosmic story and constantly interact with their environment. When a supermassive black hole accumulates matter, it releases massive jets of high-energy particles and radiation that tear through space and heat the surrounding gas to extreme temperatures. This process is not just a spectacle, but plays a crucial role in controlling star formation. The energy released by these jets can heat and disperse the interstellar gas, preventing it from cooling and condensing into new stars. In this way, black holes act as both creators and destroyers. Sometimes they promote the formation of stars, other times they stimulate star formation. The seemingly paradoxical nature of black holes as the cradle and grave of cosmic matter underlines their importance for the fate of entire galaxies. But that's not all. These supermassive black holes are also responsible for recycling matter throughout the universe. When a massive star reaches the end of its life, it explodes in a cataclysmic supernova, ejecting heavy elements into the interstellar medium. These elements, carbon, oxygen, and iron, are the building blocks of planets and even of life itself. Supermassive black holes, with their powerful gravitational pull, attract and redistribute these enriched materials so that the elements are available for the next generation of stars and planets. In a sense, black holes are cosmic recyclers, involved in the cycle of death and rebirth that drives the evolution of galaxies. Without them, the universe would look very different, perhaps without the conditions necessary for the formation of complex structures like our solar system. Another aspect of black holes is their role in shaping the cosmic web, a vast network of galaxies and dark matter that forms the framework of the universe. Black holes are not passive spectators in this fabric. Their immense gravitational fields and energetic emissions can influence the distribution and clustering of galaxies. The gravitational waves created by the merger of black holes spread throughout the universe, subtly influencing the matter around them and altering the delicate balance of the cosmic web. By attracting material and expelling energy, black holes create a dynamic environment that shapes the large-scale distribution of galaxies and controls the dance of matter and energy that defines our universe. They may be rare, but their influence is far-reaching and shapes the fabric of existence on a cosmic scale. In addition to these specific tasks, black holes could also hold the key to understanding the ultimate fate of the universe. Some cosmological theories suggest that black holes could play a central role in the collapse or further expansion of the cosmos, depending on how they interact with dark energy, the mysterious force that drives the accelerated expansion of the universe. Imagine a universe in which black holes grow uncontrollably, eventually merging and consuming all matter until nothing remains but an endless void of gravitational monsters. A grim scenario that portends an entropic death, in which the universe fades into a cold and featureless expand. But if dark energy continues to dominate, black holes could eventually evaporate and disappear into nothingness via Hawking radiation, leaving behind a universe that expands endlessly into the abyss. The interplay of these forces, black holes, dark matter, and dark energy, remains an open question, one of the greatest mysteries of cosmology, pointing to a future we can barely understand. However, not all scientists agree on the role of black holes in the cosmic endgame. Some even suspect that they harbor the seeds of new beginnings, perhaps even spawning new universes within their depths. Could it be that every black hole is the gateway to a new cosmos, a bridge to an alternate reality, emerging from the ashes of a collapsing star? The mere thought of this challenges our understanding of the universe and raises profound questions about the interconnectedness of all things. As we continue our journey through the enigmatic realm of black holes, we move beyond the mechanics of their cosmic influence into the ethical and philosophical realms that these mysterious entities give rise to. What responsibility do we bear when we try to understand and possibly manipulate such profound natural forces? What limits should we consider when exploring technologies that might one day allow us to harness the power of black holes, or even use them as a weapon? Join us as we explore these considerations and the technological challenges of the future. Our journey through the universe is far from over. It has only just begun as we search for answers to the questions that have inspired